Okay, we're going to start in 30 seconds. Okay, so first of all, thank you very much for giving us. It's a great turnout. So great to see all of you here. Most welcome. Who's never been to a Meetup before? Just want to get a sense. Okay, and who's on the Techstars, Barclays Techstars program? Okay, good stuff. On the Techstars program, if you could just quickly say what is the companies that you represent in the corner?
FlexPay.
FlexPay.
Capital-wise.
Say again?
Capital-wise.
Capital-wise. Howler.
Spatial Edge.
Spatial Edge, also data mining. Yeah, that's right. Yeah, Console. Console has got also a few people represented here. Great. Now, most welcome here. All I want to do today, we've tried to keep it, we've learned our lessons over the past, I think, few meetups that we had. We've tried to pack in too many speakers, and sometimes it was 5 or 6 speakers, and then we go into 9 o'clock in the evening. So what I'm trying to do, I'm going to do a very quick intro. So just to basically talk about the activities and so forth, what's happening, what happened and what is going to happen as well. And then I want to introduce 2 speakers today. And it's actually going to be quite interesting. So we've got people talking about deep learning applications. So who have heard about deep learning? Okay, great. So looks like most of the people here. So it's obviously driving a lot of the innovation around AI right now. So very exciting. So we're actually looking at 2 applications. One in security industries, not only security, it could be more industries, and Jasper will talk more about that. The other one is obviously looking at the mining industry. So looking at vision and all sorts of things. And Shaun, you're going to talk about that. And I'll quickly introduce you guys as well. So first thing that I want to do is, if you haven't signed up on the MIIA, well, what you need to do is you can just sign in with your LinkedIn profile. If you don't have a photo, I think there's a problem if you want to sign in properly, because it wants that. You're most welcome. Thanks. And so this is the main website. And on this website, there's actually a bunch of resources and stuff. So what you will see, specifically if you want to look at events, just on this particular page. So this page is in fact showing all of the activities over the last, I would say, it's almost a year now. So although it was founded in 2015, we actually launched it in 2016, around April, May, and a few sponsors. The first one was at Jumo, where we held the first meetup, and then from there it just grew. And we've interacted with the Western Cape government and Barclays, and Innovation Hub, and all these incubators, etc., and had the opportunity to present and participate in multiple things. As a matter of fact, there's actually a TV interview about MIIA that will be displayed on CapeNet. I don't know who watched CapeNet, but one word. Display or something. But so it's getting quite a bit of attention. We've got NASPAR's Media 24 that's seriously looking at MIIA as well to see how we can collaborate. We've got Deloitte's and PwC doing the same thing. But apart from that, there's corporates like Barclays participating. We've got IBM that's going to sponsor our first hackathon that's going to happen in September. There would have been one in June, but we struggled to get sponsors and everybody lined up. Alex Conway, and as some of you know him, he's quite active in driving that whole initiative. And by the way, if you are interested to join MIIA, this is a non-profit for the whole community. We want to transform Africa using smart technologies, specifically AI, machine learning, data science technologies. So you're most welcome. So just send an email to info we're looking at actually putting a proper team together, and we can extend the board and investors, also people that can participate as well. So this is getting getting a lot more traction, which is fantastic to see. Okay, so without further ado, so I just wanted to make you aware of this, and I talked about resources. So on this particular website, we're talking about some of the future events that's happening. So I don't know if you know about deep learning and Java. That's happening. Who's going to the deep learning and Java? Great. 1, 2, 3, 4, 5, 6. 6 people. I know they've got actually a limited, I think there's only 300 allowed people from South Africa allowed to be there. But they can actually just, that's the capacity. Yeah, so I'm going to be there as well. What we planned is actually a hackathon right the weekend after that, the 16th and 17th, and that's the one that IBM will sponsor as well. And we wanted to have one in Cape Town first, so there might be one at the same time, maybe earlier in September. Who would participate in hackathons here? Okay, let me see. Great, awesome. So we're looking at sponsors. We actually, for this particular one in June, we had a fantastic problems where we had some house data and stuff available, and we're probably going to have that for our next hackathon anyway. We had the Western Cape government involved and also some real estate agencies as well. So to make it really interesting. But anyway, so some interesting stuff coming up. The other stuff, just going back, okay, that's today's event. So after this event, you will see the presentations of both Jasper as well as Shaun will be on here as well. So you can actually access it, so you don't need to worry about that. And then the previous one, we are collaborating with a bunch of other communities, organizations in the community. And this was a recent panel discussion about how can AI disrupt industries. And we've gone through the effort to make sure that this was just a panel discussion, it was in the waterfront. But I think there were some very interesting questions and really good answers from the panelists. And these are the videos that's available. So we make that available. We also make the presentations available. So everything is downloadable. And if you go through the history, we've got all the material is there. So all the links here point, in a lot of cases, to some material. So I wanted to make you aware of that. So this page is quite handy. So without further ado, what I'd like to do is just go to my presentation and just jump to this slide. Okay, so this is the agenda. So first of all, we want to say thanks to our sponsors. So Cortex Logic is a sponsor. And we've got obviously Barclays Rise as a sponsor here, so thank you very much to them. The agenda, first of all, I've already started with the agenda, so this is a quick introduction and an update. And basically tonight is about bullet 2 and 3, and it's really the first one. Dr. Jasper Horrell, he's the founder and CEO of DeepData. So he's going to talk about that, so I'm really looking forward to your presentation. He was previously, well, he was still at SKA.
Still there,
Just, but you're actually moving out full-time. He's becoming a full-time entrepreneur now.
Right.
So welcome to the entrepreneurial world. Anyway, so and then looking really looking forward to that. So that's going to be talk about security, real-time video analytics, and learning using deep learning. So proper meaty stuff. And then we've got another application, also talking about convolutional neural networks, deep learning, specifically looking at with transfer learning to train deep neural nets. And Shaun Irwin, he's actually a lead developer at Stone 3 Mining Solutions, and I know Stone 3 extremely well from my previous history with them. So this is Stone 3 Mining Solutions, but my first company that I sold to General Electric is called Ceasing Systems, and my co-founder is Derek Moorman, and he's actually now the chairman of Stone 3 Mining Solutions. So he actually bought into that, and he's very much part of that. So Shaun, yeah, so it's just interesting how it all comes together. And we also contracted with Stone 3 in the past, not the mining solutions, but Stone 3, the venture side of it. Anyway, so that's it. So I think I'm going to introduce Jasper. Jasper, I've introduced you, so I'm just going to set you up. Welcome.
Thanks, Rob. So my name is Jasper Horrell. Currently, just for this next week or so, I'm still the general manager of the science computing at the Square Kilometre Array Radio Telescope. But the deep learning wave has sort of picked me up and lifted me away. And this evening I'll be talking about what's happened in that area. So we started a company a couple of years ago called DeepData. It's a Cape Town-based company. There's 3 of us as the founders. This is rushing away.
Well, you put it, sorry, I put it in the slideshow.
Well, slideshow's fine. We just have to pause it. Can you go back to slideshow?
Okay, so you can control it.
Thank you. Okay. Right, so there's 3 of us that started the company, and what we really were looking at was what was happening here. So this is a very scientific graph, as you can see. It says algorithms and human, and doesn't say how it's measured really too much. This is taken from the latest Google I/O conference that was just this year. And they were pointing out how when you're recognizing images, so let's say you've got a human looking at an image and a machine looking at an image, you're trying to understand what's happening in that image, how well the 2 are doing. So algorithms at the top, and back in 2010 you can see the algorithms were making kind of 30% error rate, and the humans were making, I don't know what that is, but maybe like 5% or something. And then over time, 2016, where we are now, algorithms are actually starting to get better than humans at recognizing objects and images. So when we started this company, we hadn't seen the slide, but we did get the sense that there was something happening around about this time. And that's pretty much when the company started in 2014, 2015. And we looked at what was happening in a large-scale image recognition competition that was held each year. And various teams from around the world would get together, their greatest and best minds, and to come together and try and solve a great image capturing competition. So they would give them 1 million images and 1,000 classes of images, and then these algorithms would be let loose to try and see who could win. And around about that time, people started bringing in these deep architectures, deep learning architectures. So I think one of the first ones was the AlexNet architecture. Then Google came in with various sort of inception architectures, and it's sort of gone on from there. So I think the last result from last year or something, probably the end of that blue line, I think there's about a 3% error rate in what the algorithms can do now, and they're better than humans. So anyway, we looked at this graph and thought, okay, well that's very interesting. If you've got a machine that can do something better than a human, then there must be real-world applications for this. There must be something that you can do that's useful. And so a sort of question came up, okay, so if you had a camera and it could tell you what it was seeing, like a real-time video camera, then that must be useful. You could do all kinds of things. So instead of having humans watching the screen, you can have a camera with algorithms watching the screen and then just telling you when there's something interesting. And what's interesting to you might be, maybe you're interested in wildlife, and when the cheetah arrives at the water hole, or the elephant moves off, or whatever, or maybe it's somebody climbing over your wall at home, somebody carrying your TV, that kind of thing. Like one of the nice ones is we're doing a neighborhood watch pilot with the crowd in Halfback, and they said, oh, they've got this thing where they've got a camera that looks over the water, and they want to know when the distress flare goes off at sea, so somebody's in a boat and they're drowning and whatever. So can we make our camera do that? So we haven't actually done that yet, but I think that is the sort of thing that we'll be able to do quite soon. So making the world sort of easier, safer, etc. Okay, so getting started. I've brought along sort of a box of tricks here. So this is sort of back in 2015 or so, getting going. Start off with just something very simple. I'm sure you've come across them, these Raspberry Pi devices. So here's a little Raspberry Pi, programmable thing. You can attach a camera to it, and this is a very small camera because that's the size of the device. And you see the camera's much smaller. So put this on the window, started to detect myself and the cat, the sadly deceased cat who's now moved on, but anyway, so this is actually now what the current camera set up at my house, which started off as a prototype. You can see it's very carefully designed, it's got a press stick. I thought this thing would last like 2 months or something, but actually this camera is still going strong, and to this day and this evening it will be alerting away and sending images through. So it's surprising what you can get away with just when you're sort of mucking around. Okay, so then we went from there, said, okay, well, Raspberry Pi cameras are sort of okay, but you need to do something a bit more robust. So we went out into the market and bought this highly expensive camera called a realistic-looking dummy infrared camera. So it's really just a housing. We thought, okay, well, maybe we can, it says here, fake intruders out with this realistic looking camera. Okay, that's a good little fake about it. And then what we'll do, we'll actually freak them out, because we'll make it not only realistic looking, but we'll put a camera inside as well. So inside of this is now a Raspberry Pi with the little camera mounted inside of this thing. It's all kind of plastic or whatever, but it looks fairly realistic when you put it on the wall, and does actually alert. And here's the power supply, etc. in the bottom. That was good, fine, but then my sort of business colleague looked at this and said, this is not going to really work within the market. You've got to do something better. So we gave up on actually trying to do cameras altogether and said, no, cameras aren't our thing. We're just going to do hubs. Okay. So we started off with a slightly better looking hub now, which is the same thing, a Raspberry Pi in a nicer case. This thing is actually now the Raspberry Pi 3, and it can read 3 camera streams. So you put this in your local network, it reads the streams, does some initial motion detection, does some initial filtering. Is it a shadow? Is it leaves moving? That kind of stuff. And then it takes a snapshot from the video and sends that up into the cloud, and there we do deep learning in the cloud. Okay, so that's one device. We've got another one as well. This is, of course, off-the-shelf stuff now, and this other one is an Intel NUC device, so like a mini PC. This is a Celeron-based one that can do 8 streams or so. And this is sort of 1,000 Rand, and this is not 3,000 Rand or something like that. You can get i3 and i5 based ones and do more streams. So kind of we'd solved the hardware problem. We didn't have to do cameras. We didn't have to do hardware of hubs. We could just get people to buy these from wherever, or whatever. All we needed to worry about was the software. So to turn this whole deep learning thing into business, that's sort of what happened. We started really just focusing on the software. Gave up on cameras. So sort of fairly interestingly, and when you've got a camera that you can put somewhere that just looks all the time, then you start to find interesting things. Like you come home one day and you see that there's like tractor tracks on your lawn. What the heck is this? So I looked back through the camera and eventually found this thing, and it actually was this device. It said it's a refuse collector. I can sort of see why the system thought it was a refuse collector. The system wasn't very good at that point. But clearly this was okay for sort of on the road. The next image showed it actually on the lawn, which wasn't quite as good. I'm fairly sure it was a cyclist at that point. As I say, this is early findings. I also put the camera in the house, and we've got a beagle dog, and this is it. I've got an animated clip of this as well, which sort of aimed it at the table, because we were suspecting this dog was doing weird things on the table. And sure enough, every time we went out, the dog would move the chairs physically, bumps them across, jumps onto them, onto the table, scrounges around with my wife's stuff, who's sitting over here. And then the cat jumps on as well, and they're kind of having a thing. So this is the sort of amazing thing you can discover with our system. Anyway, I'm getting a bit distracted, but that was the early days. So eventually, if you give this thing enough data, as you know with deep neural networks, you have to give them enough data. And people might also ask, why don't we just take images off the internet and train this thing with images off the internet? And when we looked at images on the internet, they're kind of not the right kind of images for neighborhood watch surveillance things. You have to take something that's sort of more realistic and more something closer to your kind of natural environment. Okay, and these are the sort of characters we find in our natural environment. Front pushers and dog walkers and fan pushers. And the system has got good now, so it can recognize these things pretty accurately. And this particular camera, which is that same Raspberry Pi sitting up in our eaves, actually does a really good job now of understanding what's happening in the street. And then you can we've got an alerting system built on top of this, and you can base rules on that. So, okay, I want to see when it's dog walker, or I don't want to see when it's dog walker, that kind of thing. All right, so this is how it all sort of fits together. You've probably pretty much understood it by now anyway, but it's a really simple concept. Something happens, the camera watches it, the hub does the first stage analysis, picks up the motion, it pulls out a video frame, sends it up into the cloud, like a secure VPN arrangement. In the cloud, we've got a GPU-based machine that does classification in the cloud and decides, okay, whatever it is, in this case it's a motorbike, says, great, it's a motorbike, I want to be alerted about motorbikes, or I don't want to be alerted about motorbikes, and then it sends something to your phone or to your computer. So we can alert either to people's kind of individual phones in your pocket if you want to know about that, or typically what we try and do is send these alerts into a control room environment. So we were very lucky early on to link up with a company in Cape Town called Verify. Simon Becker's at the back, who works with Verify. And they've been really good working with us to kind of get the system, get some of the bugs out, get it going out into the market, and also understand the potential for the system. So this is just another view of some of the bits and pieces. So we've got hub analytics, cameras, other sensors coming into the cloud, and then there's some old sort of storage thing in the cloud. We don't store the full video, we just store the snapshots, so there's not a lot of storage. Analytics and then alerting. Yeah, just some view of the hubs. I've shown you those live, so not so important. By the way, these cameras, that's just a typical Hikvision bullet camera with infrared illumination around the edges, sort of LEDs. Costs about 1,200 Rand for this thing, so very inexpensive. So pretty much anybody now, you can get analytics into your house, cameras into your house. It's not very expensive. And we try to do with the system is make it very affordable. Okay, so now we had a basic prototype. This thing was up and working. Okay, what next? Right, so the main thing is, well, of course, global domination. We're going to try and wire up the world. So you can imagine now a world where you've got sensors everywhere, and you can subscribe to alerts as you like, and some of it's kind of private data and some of it's not. Maybe the public data is, okay, the volcano's gone off in Hawaii, or a new species of fish has just swam past this camera on the Great Barrier Reef, or whatever, you know, or the air quality in Cape Town or Beijing has just reached this level or that level. And so in addition to knowing whether your house is being burgled and that kind of stuff. So in the future I see these kind of systems being able to build out into a very large scale sort of setup where people can get sort of customized alerting depending on what you're interested in. It's a bit like kind of a news service based on sensors. People subscribe to news services and you get opinions and things, but this is kind of giving you facts about the world, which I like a bit more, because it's a bit more kind of scientific. So it's not just people's opinions, it's actually showing you what's there. Sometimes what you see in your camera may not be what you want to see, and we have to sort of be prepared for that as well. But that is what's happening. Okay, so we're aiming for, within the company, kind of alerting that is useful and it's timely and it's relevant. There's a very strong machine learning focus in everything that's done in that. You can imagine here not only trying to kind of just get the basic deep learning going and all that kind of stuff, but in the end you're going to have a very large scale, kind of like supercomputer-ish system, Internet of Things, distributed sensors, lots of computing all over the place, monitoring and dynamically tuning itself as well. So let's say it starts raining somewhere, getting more false alerts. You want to kind of change the weights in the system so that the system doesn't over alert in terms of the rain, or you know. So in the end, it's going to be a very interesting big computer system that's running this whole thing, and hopefully then presenting useful information to humans who actually take decisions. Of course, there's a kind of a strong problem with this kind of thing. It's very much Big Brotherish, right? There's no doubt about it. And also, if you attach this to some sort of autonomous weapon system, let's say, this could be a problem. So, and you could teach it to recognize your family members, and you can teach it to recognize when it's not your family members. And if you're very antisocial, you could turn on the electric fence then or something when somebody that you don't recognize. So you have to be careful, I think, how we build these things. And I think that's the responsibility of the community and the people in this room. As we develop these systems, as this stuff becomes possible, to also look at the ethical side and see how we can deal with that and produce systems that are useful to humans and not sort of negative systems. All right, so at the bottom there's also sort of Internet of Things, cloud, HPC, other stuff involved with this thing. In terms of the technologies, I know some of you guys here are technical people. Obviously, there's computer vision up to the cameras. The deep learning stuff, we've actually mostly focused on cafe and using the digits thing from NVIDIA to get started. That's worked pretty well for us. We're moving sort of fairly swiftly, I think, into TensorFlow, because that seems to be the dominant framework that's emerging. And you can run like little models all over the place. You might start putting models, machine learning models that are more advanced than like scikit-learn onto the hubs, maybe some more sort of neural networks, convolutional networks. We used Python a lot and C and C++ where it's needed. And we might still get into some CUDA stuff and whatever in the future. We've got a bit of skills in that area. It's all Linux and cloud-based and lots of deployment stuff involved as well, so Docker and Ansible and things. Right, so the applications are, the initial one, the obvious one in South Africa is security. The next one that's sort of coming on quite strongly is people are interested in anti-poaching stuff, and that's a nice one to do. So we're setting up a pilot now in game parks. We've done some stuff with thermal cameras. That's looking pretty promising. And also you could do animal census, counting animals and working out what's happening in that area. Occupational health and safety is another obvious one. Are people wearing their hard hats or not? Are they wearing their safety glasses or not? Are they standing under the crane or in some area where they shouldn't be when something could fall on them? And with cameras and this kind of system, you can do that quite easily. Also monitoring production. But basically, the system is sort of so generic, and deep learning in the sense is so generic, you can actually do anything with it. So anytime you could have a picture, a human looks at it and says, that's an interesting picture, I want to know about that, or when that happens, we can train the system to do that. Now, whether it's economically feasible to train the system to do that in terms of gathering the data and all that's a sort of secondary question. But you can actually do that with these systems. It's surprisingly powerful. Okay, so these are real examples from the system, and if this was my laptop, I can actually log into the server and show you live alerts coming in. But I won't because it's Jacques' laptop. But this is a real intruder detected in Taipei, one of the sites. You can see he's been to criminal school because he knows exactly how to pose, you know. This chap was quite amusing. And then, so this alert, I think, got through to the control room within about 15 seconds or so. They immediately alerted ADT. They saw it was out of place. ADT then came and chased the guy around, and the whole thing sort of ensued. This is another site. This was up in Nangaban, and here we're detecting a thermal camera. And you can see that there's a duct there. Often the thermal cameras, they don't quite have the same resolution as other cameras. In fact, the interesting part of this whole system is the real world aspect. You get cameras with different resolutions, day and night, some are infrared, some are thermal. Sometimes there's a spider crawling across the thing, webs flying around at night, the geckos on the way. So everything happens, and your sort of system has got to deal with all of that and not irritate the clients too much by giving too many false alarms, and that's really the challenge. And sometimes the clients do get irritated. Okay, so the user interfaces, as I said, we've got something like WhatsApp, but we use the Telegram app. It's more programmable, and you can send alerts to your phone via Telegram. You get that kind of thing. This is a sort of a setup app more for the technical people, how you actually configure the hubs. So it's a little Wi-Fi hotspot that pops up. You can then log in with your cell phone or your laptop and configure your cameras, configure the network, big green tick when the VPN is connected to our server, and then we're running various Docker processes here around the camera and things. Technical bits of it. This is the alerting web interface that you typically run in a control room or any web browser basically. So here's a timeline of events going from 9 o'clock to 5 o'clock or so. And then the red ones are unseen and the green ones are correct and the orange ones are incorrect. So the correct, incorrect thing, the operators look at the picture and they say, yeah, it was a human or it wasn't a human. And they can actually help us then reinforce the classifier. So we can get feedback from the users as to what they see. And also here, then this is sort of another list of events which you can click on to get the right image. And then on this side is a whole list of sort of cameras being monitored. Okay. Right, so just to show you what it can actually do in terms of capabilities. So these are real pictures from the field, if you like. This is the person class, and just to show you, this is from, if you train up a neural network, you have your training set and your validation set. So this is from the validation set, and so the classifier wasn't trained on these images, basically. And we said, okay, show us the ones you think are people, and these are the ones that with some of the highest probability it's thought of people. And as you can see, it's people in all kinds of different states. It might be just part of a head or the back, or here it's like an arm or something. This is a thermal image, very indistinct at night. Another one here. But all of these, it was very convinced it was a person, and clearly as a human you can see it's a person there as well. So more sophisticated categories. So we've got a category called somebody carrying something big.
Like a TV.
Try to train up a neural network and just explore around what it can do. And it's very interesting to kind of to give it different data and see what it does. So it's actually getting quite good now at people carrying something big. You can imagine that carrying something big is a very diverse class of things, as just looking at these pictures. These ones are typically from one side, people carrying washing or something. But these other ones, I mean, that carrying something big is very different from that carrying something big. And so it's really quite surprising how powerful the neural network is. We then thought, okay, well, we know about individual people. In if it's more than 2 people, let's call it a group. We get a group, and in fact, straight away the classifier, the next time we trained it, got very good at groups. So clearly these neural networks can count, which was encouraging. In addition to identifying things. And I guess you could easily train it to say, okay, tell me when there's 3 people or 5 people, and actually do a proper counting without individually having to go and put bounding boxes around each object and do it in a more traditional computer vision kind of way. Okay, people with prams, so you can see the sort of class of them. It's distinct from people with trolleys. Okay, now the trolley class clearly, I mean, visually, as a human, you can see the difference, but they're not that different in terms of if you were trying to train a computer vision system to look at these things. But somehow, by throwing data at the neural network, it works out how to do it. Another class we've got is commercial vehicles. We thought that might be useful in a neighborhood watch kind of sense. You might want to know, okay, it's a resident or some commercial person coming in. So we trained it up on vehicles that look like commercial vehicles, and it's got good at that. And then this is another sort of interesting one as well, the patrol vehicles. And one of the sort of alert setups we've got is show us people coming into the neighborhood at night, but don't show us the ADT patrol cars because they come around all the time and we don't be bothered about it. Okay. So we trained the classifier to understand what ADT patrol cars are, and the other patrol cars which bring in there as well, and then not to alert on that. So that's quite a nice sort of negative application. More classes, so vehicles with trailers. See, we've got quite good at that. And you can imagine with trailers as well, you get a whole diversity of things. These are thermal pictures of horses, even the back of a horse there in the middle, so somehow knows about that. Also very, very successful, and I think the last one we got here is puck. So the puck images are typically thermal images that we've got, and quite indistinct, but all the same, it does a good job of those. So I think that's pretty much all I have to say. And I've left time open for questions. We are hiring. We're in a quite exciting phase now. So as you heard, I'm sort of leaving the SK. The reason for that is we've just attracted some venture capital funding. We haven't quite closed the deal, but we're about to, and they're coming on Friday to hopefully tell us good news or at least tell us about the next step. But in the meantime, the funders have been very positive about this whole thing, and to the point where they said, even if the deal's not closed right now, here's bridging finance, and you can run with that for a while until we sign all the paperwork. So we're very confident it's all happening, and we should have sort of funding for the next 2-3 years, at least, while we build up the business, build up the revenue. It's a volume game for us. We need to make sure that we can make these things work well in the field, and that we can have hundreds of thousands of streams, eventually maybe millions of streams, and a kind of global thing. And we're really getting interest from all over the place, actually. France has got interest, Australia's interest. And it's quite surprising to us that we go into the market with this thing, sort of a new technology, unproven, show it to people, tell them our price, and they go, wow, we want this thing. And this is sort of established players in the market who've been dealing with camera analytics for a long time. And I think the reason for that is the fact that, we're trying to do it on scale and do it cheaply. Also that deep learning wasn't available 3 years ago in a way that you could actually use it. So all these traditional systems have been built up over 15 years or whatever, have done well and have worked with more traditional analytics. But the deep learning way of doing it is just so much more powerful. So I think some combination of the two is ultimately going to be the sort of winning thing. But you can imagine it's an enormous market. There's like potential, there's cameras everywhere, and there's sort of only analytics on a few of them. And the potential applications for this are huge as well. So I'd like to see eventually kind of cameras on the Mars outpost and the lunar outpost, looking for aliens or whatever, Or maybe we have some that's on the MIIA telescope now looking for transient events, stuff like that. So there's lots of interesting things to do. Okay, so I'll stop there.
Good. So are there any questions?
Yep.
How good is it with recognizing, or if you want to tell it, alert me when you see something that you've never seen before? Is there a way to do that well?
That's a tricky one, and we try and do that in the telescope as well, actually, to try and find the unknown unknowns. The way we can currently do it in a sort of fairly simple way on the current system is when the classifier is not confident at all that it's in any of its known categories.
All right.
We say, hey, that's an unknown one. So I've got a category called In fact, the category is a really good one to train on. Because what you want to do with a neural network, it's a super powerful thing, these deep networks, but you don't want to give it stuff it already knows, you want to give it stuff it doesn't know, so it gets better. So I'm always looking for things where it's getting it wrong. That's actually the interesting stuff for us. And the category is a good one, because it really doesn't have a clue. So that's one way, but there's many other ways you can approach that as well, and it's quite a tricky area.
No, go for it.
Okay,
It's
sorry.
surprising.
Are you deciding which snapshot to send for classification from the screen?
Yeah, so from the hub. So the thing must have moved. It must have moved for a short while. Then it goes through another sort of online. There's a few other checks and balances there. But then there's a small machine learning model running on the hub that is really just checks for, does it compare with like a known shadow kind of movement or shadow setup or trees or vegetation, that kind of thing, something that we see a lot of. And that will actually give that model to all of the hubs. And then specific cameras, you can fine tune what that thing is for that camera. So if a particular camera's got a particular problem, you can tell it, no, don't show me that a few times, and then and rebuild that model. And that's a very quick model to rebuild. It's typically like a random forest classifier. And that learns very quickly not to show those kind of images. And then if it gets past that, then we send the snapshot. And then we also have some time delay between how often it sends snapshots.
So the question was, how many images do you need to feed the classifier before it gets to a reasonable level of accuracy?
I think, yeah, so we've got tens of thousands of images typically at the moment that we've all labeled as things. If we give it a new class of things, because it uses the rest of those images now to work out the basic kind of feature identifiers and things, edges and all that kind of stuff, you can train up on that. You don't need that many images, so typically like 50 images, it starts getting quite a good feel. 100 images is getting fairly good. But in the beginning, you need a lot of images just to get that kind of base level of the classifier going.
And does it use combinations to find the person with the pram? So does it end up using two separate classifiers and bring them together?
We just treat that as currently as one category.
Right.
So that person pushing pram is one category. But you can see where this is going. Of course, in the future, you want to have multiple classes or multiple tags associated with one image. So it's a white car, it's a car, it's a Toyota, it's driving on a road or whatever, you know, and have ways to deal with that in an efficient way. And I think that's the next step for us, is to how to start getting into a more kind of semantic understanding of the image, and not just a single class kind of thing. Of course, what we could do is like feed it through multiple classifiers. So you could say, okay, feed it through a thing, is it a vehicle? Yes, okay, it's a vehicle. Now, is it white? Yes, okay. But you've got to run through many steps then. You could do it that way. But I think there's more cunning ways to do it. That's where we need to hire some smart people to help us.
Very nice talk. Can you give us an idea of the dimensions of your nets? Meaning, like how many blocks do you usually separate an image into, and how many layers are required for this level of classification?
We typically, well, we don't do any of that. The net does all of that for us. So we don't segment the image up at all. We're using the kind of off-the-shelf Google Inception networks at the moment. And there's various versions of that. There's like version 1, 2, 3, and whatever. And they've got different accuracy and different training times, different inference times. But they are, I might get this wrong, but there's at least millions of parameters of weights in the network. It's a big network and very deep. And there's a lot of ways it can be tuned.
So are you just so is that the difference? You just taking exception in using that, or are you actually play quite a bit with finding that?
Yeah, in fact, just to get as far as we have, we've just taken Inception and used it. It's been really simple, so not rocket science at all. But I can see already that we're starting to explore kind of using the time sequence of images in different ways, and we'll probably move quite quickly beyond just the simple Inception thing. But it's been a good way to get started. It's got us to the point where we've got funding at least. Almost have funding.
What types of settings or classes that you struggle with?
Yeah, so that's interesting. In the beginning, you can teach quite simple things, and then you start training around the edges where it's getting it wrong. And soon you realize that, in fact, it starts to get quite complicated. The scenes get quite complicated. like there's somebody bending over or moving something, and there's another guy doing something else, and there's a car there as well. And so just having kind of simple classes doesn't work quite as well. And in addition, it's hard for the human trainer to decide what class to put it into. And that's where the human and the machine actually break down at the same time in terms of a simple way of doing this thing with simple classes. And that's where I think you start to need these multiple tags and things where you can describe the image in a richer way. In fact, the guy that's just been appointed to become the director of AI at Tesla, the company with Elon Musk, is a guy called Andre Karpathy, and he just announced today or something. He's been announced as the director. He's a young guy. He's just got his PhD, so I'm not sure how he's the director of AI at Tesla.
He's pretty good.
He's very good. Yeah, you could download his thesis, and that deals with very rich image classification, making kind of very descriptive scenes of descriptive sentences of what's happening in the image, and then also going in reverse, so kind of asking the machine, show me where the white rabbit is, and it understanding all of that and pointing it out in the image. So there's lots of cool stuff, and that's kind of obviously in the research realm at the moment, but there's lots of cool stuff that's happening that will allow us to do that. I'm not really answering your question, but basically, anything where it starts to get really complicated, and as a human you start having doubts, and your consistency of your training set starts to get running into problems, that's always going to be an issue, and that's already an issue for us, that you start training, and at the beginning of the hour you're doing one thing, at the end of the hour you start realizing, oops, I'm no longer doing quite what I did when I started, I'm putting these things into different categories, and my thinking has changed as I've gone along. And the network's quite robust to that, but eventually I find I have to refactor the data every now and again. I've got to sit down, almost like look through all of it, and you know, every 6 months or something, and redo it. You don't want to do that too often because it's a lot of data.
Fantastic. Any more questions? Yeah.
Is it possible to measure acceleration and deceleration
Of
the speed of
objects in the...
of objects moving, for instance, cars, flashing, to identify that?
You certainly can do, but not typically with the way we're doing it now. I think you'd use more traditional kind of computer vision techniques for that. Well, I would. I don't think there's an obvious way to measure deceleration or whatever, unless you had lots of images of cars crumpling and you could sort of link that back to the data. You can certainly kind of identify accident scenes and things, so that's one of the things that's happening up in Joburg. They're putting up these fiber optic networks with lots of cameras, and the insurers want to know, okay, tell us what happened when there was this accident in this claim, show us the results of your camera, and show us who was involved and how many cars, and you need to be able to kind of search through your database, find that stuff quickly, and present it.
Right. Just a quick comment. Yeah. So, more questions? Just make sure no one else. Okay. Fantastic. Fantastic talk. I just want to. First of all, I think what we're looking for is building end-to-end solutions. That's what you're doing, which is just awesome around this. You're also building some of the foundations also where you can actually, you're doing classification stuff, you can also know with your current neural nets, you can put on top of that, you can generate descriptions of what the scene and stuff like that. So this, from a roadmap perspective, there's so much to do. So good luck with that journey, but thank you very much. Okay, so next speaker is Shaun.
Yeah, so I'm Shaun. I'm at Stone 3 Mining Solutions. We've got a couple of my colleagues here with me today. As Jacques mentioned, can you maximize this?
I can, sorry.
obviously. A lot of it's in the sort of optimization, trying to use sensors, cameras and lasers, and various other sensors to try and optimize the mining process, to try and reduce energy consumption and any losses sort of along the way. And you find that even though mining has been around for a long time, there's still a lot of ways to try and improve that, especially with the sort of techniques that we've been hearing about today in the machine learning space. So I'm just going to give you sort of a brief overview of some of the projects, just touching on a few things that we're working on, especially in the machine learning space, and also introducing this concept of transfer learning, which Jasper spoke about, or he just sort of touched on some ideas, even without mentioning the name there. And then I'm going to give just a little overview of projects that I've been working on, the Tell Your Truck, and then some other work later. So we've developed quite a few sensors. We've been around for over 10 years, maybe 15 years or so. I've just been there for the last 3 years. But we've got quite a few different sensors, things such as measuring the particle size of ore. So you've got conveyor belts with ore coming along, and later in the process you have crushers and grinders that take those big rocks and make them small. And then you've got flotation cells, which are chemical processes where you try and, let's say you've got a platinum mine, and you've got, this is later on in the process where you've crushed the ore into small particles, almost sand sort of consistency, and you want to separate the platinum from the rest of the stuff. So that's what a flotation cell allows you to separate those. So I'm just going to give you a very basic overview of convolutional nets, because there are sort of something that underpins a lot of the work that we do. But I'm not going to get too technical. Some of you might know a lot about this already. But basically, you've got many layers in your convolutional nets, and that's various models of different architectures. And what's important to know is that the first layers, the input image enters on the left, on your left, and then you end up classifying on the side of the network. And once you've trained your network on enough images, you find that the first layer ends up learning something similar to edge detection, where if you set edge, so you've got some strong edges here, those will show a strong response, and they'll pick up the signal and pass it through to the later layers, and then so on and so forth for the later layers. And then later on, you start learning the concepts of faces and cars and whatever else you're busy training on. So, very simple example, if you have an ImageNet classifier that's been trained on the 1,000 classes that Jasper mentioned earlier, you probably have a donkey or a horse in there somewhere and a hat, so you might get a sort of a confidence estimate in the two different classes. Okay, now with supervised learning, which we've been talking about so far, you have this issue where if you don't have enough data, you end up starting to overfit, which is basically where you become the network becomes more confident in its estimates as you train, but you're training on an insufficient size of data, so not enough images or samples, and then you stop being able to generalize to new unseen data. So you end up effectively memorizing the training set and not being able to predict given new data that isn't within that training set. So if you remember back to maths, you've got a set of data points, and if you have a polynomial function, you fit some function to that. It's always possible to come up with a function that will fit those points, but that might end up looking like some crazy squiggle like we have up here, when in fact you want something that fits the average and doesn't try and fit the noise. And other problems that you find with supervised learning, let's say you're in the stock market business and you want to develop models that predict what some stock might do in the next week or two. You find that those models might only be applicable for the last 2 months of data or something. And the market enters a new state down the line, and those models are no longer applicable. So you start needing to try other techniques. And of course, with these deep networks, there are lots of parameters, and it takes a long time, sometimes up to like 2 weeks or more for some of the huge networks. So you'd like to try and speed up your training. So this is where transfer learning comes in. So you've got this concept of domains and tasks. So here I've got an image of 2 domains. One is, they're both bicycles in this case, or this one. But the context is quite different. So sometimes you want to sort of, you only have data, or you have a lot of data from the one domain, not of the other, but you want it to work in the second one. So you might want to sort of bring in some of that information. And same with tasks. So one task might be to segment the bicycles in the image. Another one might be to segment cars and images. But if you think about how you learn, you might sort of use some knowledge from another domain to help you with when you're learning something new. Okay, so I'm not going to talk in detail about these things, but what's important is that there are some models out there that have been trained for you. They're publicly available. Google and Facebook and these sort of companies have gone to the effort of training them. And sometimes they look quite crazy, like this one over here. So Google's 68 million parameters. And Oxford University created the BGG16, which is 138 million parameters. That's half a gigabyte storage space for that. So for you to train one of these, it's going to be quite a hard job. But fortunately, you don't have to. And in many cases, you can make use of, you can just fine-tune just the last few layers and apply them to what you're working on. Just an overview. So this graph here shows you basically computational complexity on this side and accuracy on that side, trying to classify images. So the one that I showed you now, the BG16, is very computationally heavy compared to the other one.
And not as accurate.
Sorry?
Not as accurate.
Yes, that's also quite interesting. So it doesn't show you when each one was developed, but that one is a little bit older, and Euronet came a bit later. But it's quite interesting how some of the networks, even though they might be sort of more computationally expensive, but they don't make use of interesting tricks that can actually help your learning process and give you more accurate results.
And Shaun, it's quite interesting.
Yes.
Jasper mentioned the Inception.
Yeah.
So there's version 3 and version 4. You can see I'm more on an accurate. The blue one there, what is that one?
Google Net.
No, on top, the one at the one on the right. Is that Inception 4? Well, that's Inception 4.
Yes.
That's Inception version 4. That's it.
Yes. So I don't know the details. What separates them. I assume it's the number of layers, and I'm not sure if there were many architectural changes. I'm not too familiar with those ones. But yeah, so basically, these companies have been trying to outdo each other and trying to minimize the error in ImageNet. It's a very important competition that has been around for the last few years. Okay. And then, so that was one example of the method you can use for transfer learning, where you basically use a pre-trained network, and then you just modify the last few layers if necessary. So you transfer from whatever those tasks were that, or the sort of images that were available when it was training, and you would like to apply to your own. Yeah, this is a different sort of approach. So you can also stack many layers if you want. I've just simplified and showed one hidden layer in the middle, and then the input and output layers. So you've got some handwritten widgets. And here the task is to feed the original image in as an input, and then also apply it as the output. So basically it tries to just map itself to itself. But what is interesting here, rather than just you sort of imagine multiplying by one, it's just feeding it through. You add a bottleneck in the middle. So you've got to push that information through a narrow sort of bottleneck, and then try and recover that at the end without losing too much information. So this is what an autoencoder does. It's quite an interesting way of thinking about it. And so what's useful here is that you can force it to learn the most important features, and what you end up doing is getting rid of noise in your system, the sort of parts that can't be predicted so well. You can use those features that you've learned to train your networks. Okay, so this looks a little complicated, but basically there's another technique which is really interesting that's gaining a lot of attention now. Basically trying to train a single network to do multiple things simultaneously. So here you've got a whole lot of people in the street scene, and one task is to identify what class each pixel belongs to in the scene. That's called semantic segmentation. So a person might be colored as a red pixel just to indicate classes, and ground might be purple, etc. So that's one task. Then you've got depth at the bottom. So how far away from the camera is this person, or is the road, etc. And what they find is that by jointly training this network, you actually learn features that are in common to multiple tasks. They are somewhat related. They're all vision tasks, and yeah, you can see that they're all related physically in sort of space, and that helps with the whole training process and learns sort of nice representation. Yeah, so this is, and then I think the last sort of general example I'll give of training using transfer learning is it's quite nice. I listened to the podcast, one of the machine learning podcasts recently, I think it was end of last year, where this group from Stanford, to tackle one of the UN goals of trying to eradicate poverty or minimize as much as possible. First of all, you've got to take some action on something. You need to be able to first measure and see your progress. So, but now this is quite a complex task, because you can imagine that the poorest countries in the world don't have the money to spend on statisticians and all the people in the field trying to do surveys to gather all that information. And it takes a long time. So the census data, you never see a census of this sort of scale available every year. It's probably every 5 or 10 years or something. So they were thinking, how about, we've got satellite data, it's pretty much in real time. You can have a satellite orbiting every day, or maybe faster. And sometimes it's nighttime, sometimes daytime when the satellite passes overhead. So how about trying to use the night, or try to predict the nighttime images from the daytime? And because at night you've got all the lights, and that you can use as a sort of a vague proxy for sort of infrastructure, road networks, and etc. And they found that it worked really well. It almost worked as well as censuses. In places where they had that information, that sort of ground truth data available. But then it, of course, it could be used in all sorts of other places too. So it's a really interesting application. Okay, and just to give you an idea, in industry so far, most of the advances have been in supervised learning, or at least the ones that in sort of industry where, yeah, not just the academic side. advances in academics forefront. And transfer learning is starting to become a really important thing. So you don't have to go and train your networks from scratch. You can do it much smaller budgets and smaller time. Okay, so I'm just going to give you a brief overview. Our tech stack looks quite similar, I think. Python and TensorFlow, Jupyter Notebook, some open source tools, and a GPU. It's very hard to get by without one of those. Some of the experiments that I do pretty much take a day of training just on the GPU, and it'll take about maybe 2 weeks on the CPU for some of those tasks. So for running one experiment with one set of parameters, taking 2 weeks is really not going to get you anywhere.
Shaun, quickly on the GPUs, are you using cloud GPUs or are you
no,
local?
We're currently using local.
Yeah.
We're sort of debating between the two, but
Have you worked out a cost and stuff? Comparison? Obviously, you bought one.
yeah, I think things might have changed because Google Cloud came around later, and sort of things do change a bit. But I think we're quite happy with
Yeah.
this little one for the moment.
What made you go with a local one?
Some of the data.
Security, less hassle once you have it. Yeah.
So for clients and stuff, it can help to have it. Sometimes they believe that keeping it on your machine locally is better, but I not necessarily agree with that myself. I think Amazon is pretty safe, but
I know it's more of a setting up the
also
security protocol.
sending large data sets across the network can be a problem. I mean, we're dealing with quite large data sets sometimes.
We've just done a cost comparison. We looked at the Amazon GPUs and the Google ones and the other ones we found. They're all about the same price and they're way too expensive.
Yeah.
It's a lot. Within about 2-3 months, you recover your server and your GPU and everything if you buy it locally. So if you're going to run something 24/7 in the cloud, then it's not really economical at the moment.
Yeah,
It's convenient, but it's not.
Yeah, it's good if you don't have a large budget, you just want to try a Kaggle competition or something like that, and or maybe the way I was thinking about it is have our own machine for doing sort of continuous experiments, and if we find that for this one experiment we want to try and just for like maybe a day or two or a week or something, we want to expand it on a much larger data set or something, then we can just for that period hand over to the cloud. So you don't have to try and cater for the peak demands and buy some super expensive GPU or like a whole array of them. Rather just have one that gets most, like 90% of the work done, and then if you need to, sometimes just.
What's your take-home cost?
Just 10 grand-ish with a GPU. And then, okay, the whole machine probably costs 22. So it's not like crazy.
Yeah, the cloud cost is, the one we're running at the moment in the Google Cloud, it's $650 a month.
Ah.
So it's like 10,000 rand a month.
Yeah, it would cost about that price for the GPU itself. And then you can have
That's
it.
for the CPU part as well.
Yeah. Oh, okay.
So, Jasper, would you then consider moving local or?
Yeah, we are considering setting up a local hosting with our own box. Yeah.
Okay.
When you
Cool.
say $700 a month, is that you can utilize it within that full month?
Yeah, that's because with our image alerting thing, it's 24/7.
Okay, so it is for the full month's
It's
running capacity,
running
basically.
the whole month, yeah. Yeah.
But how many CPUs are that running within the cloud?
It's 4 virtual CPUs and then the 1K80 GPU.
Okay.
So it's quite expensive.
Yeah, so I definitely think
It's
it's.
kind of a convenience. It's great.
Yeah.
for that.
Yeah. No, I
I
don't
think the
think.
cost will come down, but they're not yet.
Yeah. Yeah, so now to the mining stuff. This is a system I've been working on for the last year or so. And yeah, we're starting to deploy it at a few sites now. This one's been around on the first site for quite a few months now.
Where are you deploying?
Finland and Zambia and all sorts of
Awesome.
Africa.
Fantastic. Yeah.
Yeah, so this system is basically, we call it until your truck. So you've got your open pit mine, which is out of view, but basically you do all the blasting, and it doesn't matter what sort of ore type it is, copper or whatever. And these big trucks go and fetch the ore, and they dump the ore into the primary crusher, which is the first crusher of the plant. And the thing is, sometimes you got huge rocks coming in, and they seem to have a competition to see which truck can carry the biggest rock and can't break the crusher. I mean, I wanted Jacques, maybe.
Yeah, I'll quickly.
It's quite impressive just how big these trucks are. So you can't really see it from here, but from this sort of wide angle view. But these trucks are carrying about 180 tons of rock in one load.
Here we go.
This is sped up by a factor of at least 2. So that width there is about 9 meters. Yeah.
In my
It's pretty
driveway.
big. And then there's this, you call it a pecker. The crusher is right down below. Yeah. And that just assists the rocks should fall in, but sometimes they get a little bit stuck and helps them go into the crusher. Yeah, so there's some large trucks. And yeah. Yeah, so it's quite a simple sort of setup, but you'd be amazed at the variation that you can get in what happens here. And we have a live feed, so you can see on a day-to-day basis what's going on. There's the occasional crazy things, but weird vehicles that you didn't know about, and suddenly that's in your view, and you've got to sort of create a system that's capable of detecting all of these things robustly and not just all of it. We're not we monitor it from time to time, but you can't sit and watch it all the time. So we want the system to be quite robust. Yeah, so basically we're trying to measure the size of the rocks as they come in, and alert do sort of whatever actions where they stop the system if a massive rock comes in to prevent it from crushing the crusher, or various. And you can see quite a large truck. So when I stood next to it, the midpoint of the wheel is above my head, so it's quite large. Yeah, so we've got all sorts of conditions. This one's in the Arctic, so we've actually got snow and some ice and rain, dust, all sorts of things. And the lighting, the sun comes back from behind, and you can see that you saw the pecker earlier, so it creates these dinosaur type shadows. It's quite weird. Yeah, so it all adds to the complexity of the task.
Now it's slideshow mode.
Okay. Yeah. So one of the goals or aspects of the project is to figure out when the truck meetups. It's quite a cool component. And originally, I was trying to use sort of the old school image processing techniques to accomplish this, but I found that it was working perfectly for maybe 2 months or something, getting 90% accuracies. But then you find that the lighting changes, and there are all sorts of other changes around there, and it becomes hard to sort of find a set of parameters. Even though the algorithm isn't all that complex, it becomes a really complex task to try and find a single set of parameters that works in all situations. So that's where I started trying out the machine learning approaches using convolutional nets things. And I found it wasn't immediately easy because there's still a lot of playing around needed. But once you found something that works well, then that is extremely robust. And yeah, I found that that's been working for the last few months very well, and using a wide range of conditions and things. And yeah, so you can see why there's so much hype around deep learning, and it does really work really well if you have the right sort of problem that you kind of tackle. And one problem here that's the next sort of stage in the problem is to identify where the back of the truck is, which parts correspond to ore. And I found that if I made a mistake in the choosing when the truck is tipping, then it will throw the next stage out. So you can see over here the bounding box is showing wheels. Yeah, so just one other application. I won't go into detail about how this works, but just to give you sort of an idea of what's another thing that we're working on. So flotation cells that I mentioned earlier, we try and using a chemical process to separate your platinum from the rest of the stuff. One important piece of information in trying to model those chemical processes is the size of the bubbles that you have. So basically you've got these big tanks, and they could be several stories high. And you've got this sand, sort of containing platinum and other things, pump it into the tank. You've got some water and other things in there, and bubble gas from the bottom. And using special chemicals and stuff, the platinum will cling to the bubbles and rise to the surface, and you skim that layer off, and the other stuff will sink down. And one important thing to measure is the size of bubbles, to get an idea of how much platinum you're recovering and how to optimize your processes to improve that. So I've applied deep learning techniques to that to automatically identify the bubble structure, because it's quite hard to figure that out using the old school sort of techniques. We've tried that for a long time, and it gives you some away, but the deep learning techniques are very promising. So we're quite excited to see how that turns out.
So Shaun, I'm quite curious on this one, because C-Sense Systems, I don't know if you know, we actually had a technology, Frostmaster, that we sold to Outokumpu, Finland. And Derek knows about this because he was part of his PhD as well. But so it would be interesting to compare this now with deep learning with that.
Yeah.
I'm sure Derek would find it very interesting.
Yeah.
That's right. So previously we were using like the more geometrical approaches like watershed.
Wow.
But that quickly runs into its limitations, and this is still a fairly easy sort of scene, but it can get complex quite quickly, and that's where we are trying to improve that now.
Awesome.
Using the machine learning approach.
Cool.
Yeah, so you can, similar to the truck images I showed earlier, you can also get daytime ones. These are all with the night images. You've got a single light source, so you've got these nice single points of light in each bubble, so you can imagine you can use that information in an algorithm. But sometimes if you've got a light source with the sun coming from the side, some shadows moving over, it becomes quite complicated. Blur, there's some blur in the top one there. There's a lot of variety in what you have. So that's where you get a lot of robustness from deep learning. Yeah.
I'm just curious, what does the training data look like? What do you give it as output? What are you trying to get the network out?
Yeah, so I forgot to mention that actually. Thanks for pointing it out. So as a sort of preliminary step to calculating bubble size and distribution of that for a single image, if you can determine the outline of the bubble, you can't obviously calculate the complete or board up a 3D model from a single view. You can do things that can infer it using prior information and things. Or if you have stereo cameras, you could actually create a 3D model of the surface. But for cost reasons, we just have a single one. You've got maybe 30 of these massive tanks on the site, and so it becomes expensive if you have fancy sensors. But so what I'm training here is to look for the edges. So we have another algorithm which will generate those edges and then use that as training for this. Yeah, sometimes manual drawing. You're trying to minimize it because it's imagine creating ground truth for that.
6 months.
Took me, I don't know, a few ground truths just for testing the accuracy of the system. It took about 30 minutes in the image for when you have small bubbles.
Yes.
And the intermediary layers of the Google didn't work? Wasn't actually good enough?
I haven't tried that one yet. Still early days with lots of other things to try. Yeah, we find those networks sometimes they're better for classification than for segmentation. They don't have sort of the inherent structure that you would sometimes want. But there's some modern techniques that work nicely with it.
For like your normal images like yours, so it's
yeah. So if you classification, you're just trying to find a class for an image. So whether it's a car, yeah, we want to feed an image and you get an image out, which is one of these.
Do you measure the individual sizes of those to get some sense of a ratio of the size?
So the following step, yeah. So yeah. So essentially, from these images, you would then have another algorithm which will take that and generate your distribution.
Cool.
Yeah.
We've had a lot of questions already during
Yes.
the talk, so I'm not sure. Are there any more questions? Okay, I think that concludes it. So there's a lot more food left. There is definitely wine and drinks and juice and stuff. So thank you for coming. And it's also about social networking and stuff afterwards. So please feel free to just stay and talk and so forth. So thank you very much.
Sounds going your way.
It looks like you can do
everything. No. It's not against it. We did consider it because
So he's involved in like
But do you have an agreement that you can't take on the decision, or is it like I was saying we own say, does it make sense to stick it out in the jam versus to take that decision? You know what I'm saying?
No, I know. Like
Hey, James, a lot of things. I got
So I have but also like
they realize that at some point you're going to have to they realize that. Just make it hard to stop. It's too long. In all honesty, I think the market is much more volatile.
You know what?
I'm an analyst. I have to I use
Oh yeah.
Actually, also science the
all the programming and be happy with that position
No, that's fine. Like, as long as I can
yes, easily, but exactly. Exactly, because the key is what I would that function is 0%. It helps.